Okay, welcome everyone. It's my pleasure to introduce Thomas. He's going to be telling us about Verlinde's formula in logarithmic conformal field theory.
Yeah, thanks, Flor. Thanks for inviting me again. Yeah.
You will always be an honorary organizer.
Am I really an organizer?
Honorary, like.
Yeah. That sounds good. That's very kind of you. Okay, so I'll give an overview talk and I made slides, so I hope it's convenient to follow. And so first I hope it's not too basic, but I want to tell you a little bit about a history of tensor categories in VOA. And for me, always the guiding principle has been Verlinde's formula. And so now I do have a good understanding of it in the logarithmic setting. So this is why I give the talk then. How do I? Okay. So first of all, we start back in the old days. You all know, or probably, that vertex algebras are coming from two-dimensional conformal field theory, and conformal field theory you can make up in every dimensions, but it's in particularly interesting in two dimensions. And the reason is, while in higher dimensions, the algebra of local conformal dimension is just finite. In two dimensions, it's two copies of the width algebra. And the width algebra admits a central extension to the Virasoro algebra. And this is why Virasoro algebra appears in conformal field theory. And this is why, and this means in particular, you should think about the two-dimensional conformal field theory as something that at least admits an action of two copies of the Virasoro algebra. And then one, of course, wanted to formalize that in some way. And we all know that vertex algebras have been extremely successful in connecting different areas of mathematics. And really, one should say that two-dimensional conformal field theory has been really successful as a guiding principle to connect many areas of mathematics, one of them being vertex algebras. And one could come up with many areas, but if we talk about this Verlinde type story, then we think about it as the connection between vertex algebras, modular forms, and of course the representation theory, the tensor categories of vertex algebras. So we have this gadget that should kind of give us the philosophy, the intuition of what's going to happen, which is the two-dimensional conformal field theory. It's chiral algebra, which one should think about as its symmetry algebra, is the vertex algebra, better said, a left and a right moving vertex algebra. Now, a conformal field theory is supposed to be defined on any Riemann surface, and then if you look at the conformal field theory on the torus and only allow for the insertion of a single field, then you get vector-valued modular forms. And these vector-valued modular forms should, of course, correspond to models of the vertex algebra. On the other hand, quite a while ago, Moore and Seiberg, they tried to axiomize what they think about conformal field theory, and eventually that was translated to the notion of a modular tensor category. Right? 2RF was very leading in that. And so in particular, one should see this a rational conformal field theory via the Moore-Seiberg axioms, equations, defines a modular tensor category. And that means a good theory or a good mathematical theory of rational conformal field theory should incorporate some structure whose representation theory gives modular tensor categories. That would be kind of the first consistency check that the mathematical idea is indeed following what physics wants. And now one can think about connections, and the Moore-Seiberg equations in particular imply that if you move a field in a certain prescribed way, around the A cycle of a torus, that then this field changes by then the corresponding character changes by its modular S transformation. On the other hand, if you think about it in a TFT type sense, then this move corresponds exactly to the open Hopf link. In particular, and if one combines this, it in particular means the Moore-Seibach axioms imply directly that the modular group actions on the tensor category and on the torus one-point functions are the same, and in particular, Verlinde's formula is the same. And I will start by explaining that. So first of all, probably you have never seen a slide like this. So this is a definition, a short summary of what a vertex algebra is. We all know that. And we know that there's a similar notion for modules. And if a physicist is interested not in the vertex algebra as such, because that's the chiral algebra, but in the true fields of the conformal field theory, and these are the fields that intertwine between different modules, so they are what we call intertwining operators, and they define the tensor product on the category of modules. But that is more the philosophy. We know that they only do this, or at least we can only prove that they do this if suitable finiteness conditions hold. Now, because intertwining operators are not given in terms of integral powers of the insertion,
Thomas, can you hear me? Oh, sorry. We lost you for a second, I think. Yeah, okay. You're back. Nice.
I'm back. For how long did you lose me?
Just a few seconds. You were just talking about insertion points and non-integer power.
Yeah, it is saying here that internet is.
Oh yeah, you froze again. I'm sorry. Let's see. We'll wait for a few minutes. We still cannot hear you. You're back now. Yeah, you're back now. But I think, yeah, your connection may be a bit unstable.
Yeah, it said it is unstable. Now, this is stupid, right? I'm at the university. It should be stable here.
You would think so, yeah.
Could you turn off your video feed and just rely on the
we could try that
slides, and maybe that'll use a little less bandwidth or something.
I'll do it, Thomas. Don't worry. Yeah. So
I can also wait. I will switch the Wi-Fi one for one moment because there are two. Let's see whether the other one is better.
Okay, sounds good. Thanks.
Okay, now I'm. Okay.
We can hear you. I turned off your camera, and I think that will help.
Yes, so now I'm also at a different Wi-Fi of the unit. They have two nets. So
gotcha. Okay.
It's unstable. Maybe the other one isn't.
Sounds good. Thank you.
Yeah, I'm sorry. This is anyway. It's the university's fault. So the fields in the physics sense are the intertwining operators, and intertwining operators because now the product of two intertwining operators is not a rational function in differentials of insertion points, but there can appear fractional powers and worse. And so in particular, a priori, it's not totally not clear that you get the same answer if you apply intertwining operators in different orders in any way, and you don't get the same answers, but that translate that in fact the intertwining operators define a tensor product, but it's only commutative and associative up to natural isomorphism. So you get a nice but non-trivial tensor category, and commutativity up to isomorphism is what we call braided. And it always should be a ribbon category, but that is usually very difficult to show. Now, in a ribbon category is very nice because there one has a graphical calculus for morphisms, and that's very pleasant because that means instead of drawing writing down formula for morphisms or drawing commutative diagrams. You just draw graphs, and in order to have a good overview, you color them in different colors. So that means each object you give a color, so the strand just amounts to the identity. A coupon then indicates the morphism from one object to another one, and that visualizes nicely morphisms. And if you have the ribbon structure in particular, means you have an evaluation and co-evaluation, so you can take traces, and so that means the number that you assign to a morphism, the trace is characterized is visualized by a circle with a coupon for the morphism included. Tensor product is just two strands next to each other, and the first important thing is that the braiding morphism that goes from x times y to y times x is where the strands cross each other, but you have here the overcrossing of the left over the right one, so which indicates the braiding. The inverse braiding would be the undercrossing. Okay, and now kind of what we want to go to is that not only have you modular group actions on spaces of modular forms, but also in a categorical sense. So the modular group, I'm sure you all have heard about it, is SL2Z or PSL2Z, and it's so well known because it acts via Möbius transformation on the upper half of the complex plane. And that in particular, it means it acts on functions on the upper half of the complex plane. And if these functions are well behaved under this action, then one calls them somehow modular. And what means somehow modular? Usually it means a vector-valued modular form and a little bit stronger vector-valued modular function. So what that means is you have a vector space that carries an action of the modular group, and then a function is on this vector space, and the upper half of the complex plane is said to be vector-valued modular form for this if the modular S transformation via Möbius transformation coincides with the action of the modular group on this space. And if you a little bit more generally, a modular form would be if there would be some additional prefactor corresponding to weight, and then there are often some additional data. It's not so important. The important thing, you have vector-valued modular functions or forms are the things that appear in conformal field theory. Right, and the reason for this is, well, we now all know. If we want to get a torus, we take a sheet of paper, we first glue two sides of it and then the other one. And now, more general, we can take a parallelogram. And now one is not interested in all tori that one can get, but only in tori up to conformal equivalence. This, or another way to say is they are up that one wants to look at equivalence classes of tori, where each class, all members in one class have the same marked complex structure, and they are precisely have one representative that is of the form C modulo Z plus Z tau. So that means the equivalence classes of complex tori are characterized of elements by elements of the upper half plane, and in fact modulo the modular group action. This means in particular that a function on the upper half of the complex plane descends to a function on a given torus if it's modular invariant. And that's why in physics you would expect that you get modular functions if you look at certain properties and certain quantities, and by certain quantities I mean correlation functions on the torus. For that, the simplest example would be if you simply look at a one-point function, so just a field inserted at one point. In that case, it turns out that the corresponding correlation functions is independent of the insertion point, and you get just a quantity which which also the VOA people call a torus one-point function. And well, the axioms of conformal field theory suggest that this should always be, these should form vector-valued modular forms, which indeed has been proven by Zhu for rational C2 cofinite, blah, 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 VOAs. Okay, and the axioms of Moore and Seiberg, and which is what Verlinde argued. So here I have the red cycle is the A cycle of the torus, and if you insert a field and transport it in a well-described way along this circle, and well-described means by thinking about the one-point function as a limit of a torus of a two-point functions corresponding to a fixed module, transporting this two-point functions once around the circle and then take a coincident limit, and then your character, your one-point function, gets transformed into the S transformed one. And the idea and this via the Moore-Seiberg axioms, one can also translate into a completely categorical operation in modular tensor categories. So this is all a review of history, and maybe just to put all this in context, and it's simply true, I think, that in the 80s the physicists have had observations that completely founded the area of vertex algebras, and Verlinde somehow had simply the observation that, I mean, he had this physics intuition by transporting one-point functions around the A cycle, gives a modular S transformation, and why this has something to do with fusion rules. And so that means he came up with a conjecture that modular S transformation captures the fusion rule, and he checked it in many examples, and that's all looked very true. And a little bit later, Moore and Seiberg were much more conceptual about it, and came up with a system of consistency conditions for correlation functions of conformal field theory on Riemann surfaces, which are now known as Moore-Seiberg data, and translating that led to the notion of modular tensor category. In particular, if you want to take a VOA standpoint, a VOA should have properties that correspond that correspond to Moore-Seiberg data in some sense, and that's really the standpoint that E.G. Huang has taken. So so for a mathematician, somehow that was in the late 80s, and now for a mathematician, the idea was to define an object. Well, this object is now what we call a VOA, that has a structure that obeys the Moore-Seiberg data. So and indeed, E.G. Huang, right, he was looking at strongly rational vertex operator algebras. So that means VOAs that are rational, C2 cofinite, Z-graded, simple. Did I say CFT type? And its own contragradient dual. So they are C2 cofinite and rational plus standard conditions. And then he was able to carefully see that under these, let's say, good finiteness conditions, indeed everything that Moore and Seiberg proposed holds. So, and in particular, that a category of strongly rational VOA modules is always a modular tensor category. That means a finite semi-simple ribbon category with a non-degeneracy condition. And the highlight that kind of visualizes this success is that Verlinde's conjecture is true, but it's in fact just a consequence of the true thing that E.G. did. Okay, and now you of course would like to repeat everything for more general classes of VOAs, and this is probably what one really wants to do. But even the physicists have no idea what how one should really axiomize logarithmic conformal field theory. So it's I mean, it's clearly a problem that leagues more difficult than the rational problem, and so it's maybe a good idea to simply focus on a concrete statement that is very that's kind of where it's clear that if you understand it, you have done a good portion. And I would say David Redout and I, we decided that for us a key feature is Verlinde's formula, because it's something very concrete, very checkable in examples, but extremely sophisticated. You could say a Verlinde formula you only get if you at least understand that your notion of VOA is a good notion in the physics sense in genus 0 and genus 1. So that means that's already really a lot. Okay. Now, Verlinde's formula itself is something that is a triviality in the categorical sense. And that makes it maybe kind of so interesting. It is super sophisticated in the VOA sense, but not in the categorical sense. So let's review this. You need a category that has an exact tensor product so that you can have a notion of its Grothendieck ring. And then you define the Grothendieck fusion rules, or just fusion rules as you like, as the induced product in the Grothendieck ring via from the tensor product of modules. Of course, in the semi-simple case, this is equivalent to knowing the exact tensor product rules, and in the non-semi-simple sense setting, this is weaker, and one would like to know the actual ones. But I think there's a very clear path how to go from Grothendieck ring to actual tensor ring. So this is kind of okay. Now, the point is that so a modular tensor category is, as I said, a finite semi-simple ribbon category with a non-triviality condition called trivial Müger sensor or factorizability. And what that means is, if you take any two simple objects, you can look at the monodromy, that means the double braiding, which is a morphism from object times object to object times object, so that you can close it, take the trace of it, and you get a scalar. And so this gives you a matrix of size, the number of inequivalent simple objects. And this factorizability condition is equivalent to this matrix being non-degenerate, this matrix being invertible. And it's not such a hard argument to show that whenever this matrix is invertible, that the vector space that is spanned by the inequivalent simple objects, so that is indexed by those, via this Hopf-link and via the ribbon twist, inherits the structure of a vector-valued modular form. I mean, a representation of the modular group, I mean. On the other hand, simply the graphical rules in ribbon categories tell you that, well, if you don't take the full Hopf-link, but only the open Hopf-link, then, so that means you only close it on one strand, then it becomes a morphism on the second module. And so if you take two different open Hopf-links, you have two endomorphisms that you can compose. So the which is here indicated on the left with the red and blue one. And the rules of graphical calculus tell you that this is the same as taking the open Hopf-link with the tensor product. So that means that this formula holds that the composition of two open Hopf-links is the same as the right expression, as the direct sum over the fusion coefficients of the open Hopf-links that appear in the tensor product. In particular, now I can close the left and the right of this formula. And first of all, this statement can be rephrased that open Hopf-links define one-dimensional representations of the fusion ring on irreducible objects. But now if I close this formula, the left and the right, I immediately get the formula that is given here. That normalized S matrix entries, so normalized by the identity S matrix index, they obey the fusion rules of the the Grothendieck ring, which is exactly the statement that they give you one-dimensional representations of the fusion ring. And by the way, these normalized S-matrix entries one also calls quantum dimensions. Now the invertibility comes in the game, because we see, first of all, one of these S1, R in the denominator we can cancel on the left and right, and then if we can, S is invertible, we can multiply by the inverse, and we get a closed formula for this fusion coefficients. And this closed formula is called Verlinde's formula for fusion coefficients, and the Verlinde's formula in the tensor categorical sense is nothing but the argument I sketched, and so in particular you would learn about it in a lecture on modular tensor categories for sure. It's not that complicated.
Can I ask a question in the previous page? The R here in the modular tensor category, is that a specific object?
It's just for any simple object.
Just take any simple object, one is the tensor identity.
Yeah, exactly. And R is just any.
Okay, thank you.
Now we can also go to the character side, and we know the character of a module is just the sum of its graded dimensions weighted with q to the n. And here, of course, for modularity reasons, you normalize with q to the minus c over 24, where c is the central charge. In any case, in the strongly rational case, Zhu has proven this modular transformation formula. Has proven that the character vector and more generally the torus one-point function vector forms a vector-valued modular form. In particular, we have an S transformation of the type that I wrote down here. And the consequence of all of EG's work, and actually the highlight of his work, is that this torus one-point function S agrees with the categorical S, with the Hopf-Link S. Okay, so this is my motivation. And now we want to, or maybe the starting point, and the general hope is that just generalizes. And it should generalize just because, at least it should generalize if we do VOA theory that has good connections to conformal field theory. Now one has to say what kind of categories one is, or VOAs is interested, and for me the best situation is actually non-semi-simple but also non-finite. Non-finite means you have more room to play, and you in fact it turns out non-finite is in quite a few senses. The good non-finite categories are actually quite well behaved. So on the categorical side, the open Hopf-Link has nothing to do with semi-simplicity. That's fine. A technical challenge for VOA theory is rigidity. This is somehow a nightmare, but we made progress on it, we all. Because we are not finite, then we don't want to talk about an S matrix, but an S kernel. So this means really a function that depends on the labels of the modules. And a sum we will then replace by an integral. So that means we also need, of course, a good notion of a measure on the space of objects. But these are things that are okay. The point is, for a long time the VOA situation seems to be unclear, or at least it seemed to be quite unclear how to prove it. And I will illustrate the problem in the example of SL2, because it's one of the two examples where we can work everything out. And also because that's probably where my interest on this problem comes from. So 12 years ago, maybe it was also 13 years ago, I met with David in Canberra. So at that time he was still in Canberra. And we chatted about the Verlinde formula for SL2 at admissible levels, so affine SL2 at admissible level, because at that time the situation was that in the 90s physicists had looked at it, and they did computations that didn't make any sense, and then their conclusion was that the the conformal field theories are intrinsically sick, so they didn't have the conclusion that maybe they should have thought more thoroughly about it, but that the theories are bad. In any way, so 20 years after the physicists gave up, David and I revisited it, and we kind of saw, we saw what the physicists did as misinterpretation and got a consistent Verlinde formula. And then, of course, it was the task to develop a good enough theory of vertex algebras that then proves this Verlinde formula. And that goes, and this is now what I have, and I'll state at the end of the talk. And it benefits, of course, of things I did with David, but then also Shashank, what we all with Jinwei and Robert did on vertex tensor categories, and then also later I did a lot on categories, and I must say with Simon Lentner I have learned a lot. So to give a little bit of credit to some people. Okay, SL2 we know what it is, and I think I use standard notations or standard basis, commutation relations. Kappa stands for killing form, normalized in this way. It's important also to know the explicit form of the Casimir element, right? So it generates the center in the universal enveloping algebra. And then we do representation theory. And one thing is that we all do now, namely we know for every dimension, SL2 has exactly one irreducible representation. But then if I take a non-positive integral weight, then I will not get a finite dimensional irreducible highest weight representation, but I will only get infinite dimensional ones. These are the objects in the category O. They are also well known. Of course, I can also look at lowest instead of highest weight modules. I would get infinite dimensional lowest weight modules. The point is one can relax this further, and this is why people called it relaxed highest weight module, to just get weight modules. And I think it's better to call them weight modules instead of relaxed highest weight modules, because they don't have a highest weight. So then a name with highest weight in it is not the best. And these are maybe a bit less familiar, so that's why I'll give you an example here. So the underlying vector space is infinite dimensional, and it's just indexed by a translate of the root lattice. So the root lattice of SL2 is identified with even integers. And now you want to give it the structure of an SL2 module. The first thing is you fix the action of the Casimir. You say it acts by a certain fixed scalar that you call delta, and H acts on a weight vector by its label. E changes the label by plus 2, and this completely determines the action of F, because F, so these are now the last two lines, because F acting on such a vector we can write as F times E acting on the pre-image of E, but F times E using the Casimir we can express as an expression in terms of Casimir and H, but we know how they act on weight vectors. So that means if I introduce the action of Casimir, H, and E on the module like this, the action of F is fixed, and it's given by this formula. Now, already for the finite dimensional Lie algebra, you can, because tensor product is multiplicative in the weight spaces, you immediately see that the tensor product of two such weight modules has weight spaces that are all infinite dimensional. So it's not, the tensor product will never be a finite sum of weight modules. And that is kind of a big warning, right? How can you expect a good vertex tensor category if the corresponding category of modules of the finite dimensional Lie algebra is not well behaved? In that sense, it should maybe be taken as a surprise that the VOA works so well. So the VOA will work very well. Anyway, we recall the formula of the action of F, and we see it acts on a weight vector of a given label by a certain scalar and changing the label by -2. So you see, the scalar can vanish or cannot vanish. If it never vanishes, we obviously get an irreducible module, while if it vanishes, then we get an indecomposable module with 2 composition factors. And the way I constructed it, it will have a submodule that is lowest weight, that's indicated with this minus, and a simple quotient module that is highest weight. Okay. Next, we turn to the vertex algebra. So now we have studied a little bit what happens for finite dimensional Lie algebra SL2, and we know if we have a simple Lie algebra and we fix a bilinear form, then we can affinize it, and if we have it affinized, we can construct a Wörmer module or better Weil modules. But for that we better specify also the action of the center, which we call the level. And we know in particular the Weil module corresponding to the trivial representation can be given the structure of a vertex algebra, the universal affine vertex algebra of this given level. And by L, I will always denote its unique graded simple quotient. And the aim is to study representation theories of the simple affine vertex algebras at suitable good levels. And we kind of know what suitable good levels is. We already know from the olden days that the Westermine-Witten models, the positive integer levels, are rational VUAs, and that these are the only rational affine vertex algebras. The next best thing is admissible in the sense of Katz and Wakimoto, which simply means that the level is rational and positive enough. And this admissibility comes from the fact that an admissible means that this Cauchy-Lustig polynomials and the resolutions have the multiplicities are all 1, so that you get immediately good character formulas, and that means good modular properties. And good modular properties are your indication of a good representation theory. Okay, and I would like to look at these admissible ones, but restricted to SL2 because everything else is too complicated at the moment. So what one wants for a module, one wants it to be graded by weight, by the G weight, by the Cartan subalgebra, and by conformal weight. And you want to impose some finiteness conditions. So and the ones that we want to impose is that the bi-graded weight spaces are finite dimensional. And otherwise nothing else except that it's a module for the VUA, which translates to that it's a smooth weight module and actually a module for the simple affine VUA. So to give you an idea what happens, so the admissibility condition for SL2 is simply that the level is rational such that k plus 2 is a positive rational number with a numerator at least equal to 2. And then we can take any finite SL2 module, induces to a module of the universal affine VUA, and then take its simple quotient. Now the simple quotient, so you can do this, for example, for an integral module Rn, but you can also do this for a weight module E lambda comma delta. And whether you're induced the simple quotient of the induced module, or I should better say almost simple quotient, is a module of the VUA depends very much on your choice of Casimir eigenvalue, and it turns out there's only a finite set of Casimir eigenvalues labeled by Virasoro minimal model indices, such that the induction in this sense is a simple module for the affine VUA. So these are very few, but they all appear. And if they appear, their appearance only depends on the Casimir eigenvalue. The weight label is always okay. So almost semi-simple means that the corresponding module only has every non-trivial submodule intersects the top level. Now, one point is that these modules are not all, and the reason is that an affine Lie algebra always has an automorphism group given by Weil translations, by the so translations to the translation group of the affine Weil group, and that doesn't leave the horizontal subalgebra invariant. So we see this here, that it changes the mode index of the modes. In particular, also it doesn't leave the Virasoro zero mode invariant. And whenever you have an automorphism, you can twist the module by the automorphism, which gives you, as a VOA module, an honest new VOA module. In particular, these spectral flow twists of lower bounded modules are almost never lower bounded. And actually, David drew this diagram 12 years ago. This indicates that, so for example, the top line in the middle indicates the Weil module, or the simple quotient of the Weil module corresponding to the two-dimensional representation. And here you see, if you twist it by spectral flow or you inverse, you get an object on the category O plus or minus. But if you twist it twice, this indicates it's not lower bounded. Similarly, in the second line indicates how spectral flow acts on objects on the category O, and the last line on categories in the weight modules. What it in particular wants to illustrate is the vertical axis is the conformal weight axis, that spectral flow twists are almost never lower bounded. So that means you have many modules that you don't get naturally, at least not very naturally, from the finite dimensional Lie algebra. Next thing are characters. Well, characters turns out one can work out, and it turns out for these weight modules, they have a very similar form. They have in particular, they have is up to normalization. So this Y and Z you should just take as normalization. They are Virasoro minimal model characters, this chi-RS, so in particular something that corresponds to a nice finite vector valued modular form divided by n Dedekind eta squared, that is nice and modular, but then multiplied by a sum like this. And this sum, well, that actually only converges in a distributional sense. So you should think about it that the weight modular characters are distributions. Now this character formula can be by now easily discovered once one knows that the simple affine VOA of SL2 at these admissible levels, at the non-integral admissible levels, embeds in the corresponding Virasoro minimal model times the Adamovich pi. And in particular, these distributions are characters of this Adamovich pi, which is somehow is nothing but an extension of a Heisenberg VOA, just maybe a little bit unusual, but it has a very easy representation theory. In particular, it's semi-simple in the category of weight modules. And in particular, it's a very easy exercise to see that the right-hand side, Virasoro minimal model times pi, is a representation category that admits a very nice and semi-simple Verlinde formula. So, I like to call the program maybe an inheritance program, because this is what, so one is kind of fishing for tools that can tell you what's going on. And here we have the situation. We have a VOA we are interested, SL2 at admissible level. We have a VOA we know, Virasoro times pi. Now, and it's a conformal embedding. In particular, if we knew SL2, then the theory of VOA extensions would allow us to relatively easily understand Virasoro minimal model times pi. But we want to go in the other direction. That's a very hard direction. And so the point is to develop a structural theory that kind of allows one to go from easy and nice representation categories of VOAs to interesting ones. Okay. Now, the starting point of the whole story is this theorem by David and me, and that's just on the character level. We understood that you can make sense of modular S transformation of distributions, but of course you have to take an integral, and so we get some kind of continuous modular S transformation. In particular, we get and the T transformation is just given by e to the conformal weight. So that's nothing special. And this S kernel is just some function depending on the labels. Now, the problem is this formula only includes the weight modules and their spectral flow images. It doesn't include their simple quotients. And their simple quotients simply don't have good modular properties if you treat them honestly. And so you need an idea, and our idea was to resolve them. What's the idea of resolving them? It means the idea is, or maybe better, the observation is that every simple module admits a resolution completely in terms of the good modules. Let's call them the typical modules. I mean, by that I mean the weight modules and their spectral flow images. To give an example here, the LR0 is the while module corresponding to the r-dimensional representation, I mean simple quotient, and it admits a resolution, that means a long exact sequence, where all terms are spectral flow images of weight modules except the very first term. In particular, on the level of characters, it means, and characters viewed as formal power series, it means the character of the simple module is the alternating sum of the characters appearing here in this exact sequence. And so this means we have a formal identity of characters. In particular, what we did is we replaced characters by Euler-Poincaré characters of the resolutions. This didn't converge, but there was an obvious regularization scheme that was applied. And then with this obvious regularization scheme, we had expressions for S-kernel entries also corresponding to simple modules. And then we took the usual Verlinde formula and replaced sum by integral and computed this integral against the characters as test functions and got indeed a non-negative integers. So that means we got non-negative integers can be dimensions of spaces of intertwining operators. So that in particular we got a very sensible answer. And now all that had to be done is find a proof why our formalism is correct. To give you an example how such a resolution looks like, and the formulas become a little bit less complicated if one looks at quantum dimensions. This is why I wrote the Q there. For the S-kernel, it's a tiny little bit better. So what turns out what the best thing is to do is to introduce two variables. T just corresponds to which term in the resolution the corresponding entry corresponds to, and Z is the observation that that modules are also graded by spectral flow index, and spectral flow index respects fusion of the free field algebra, and so so that means it's definitely that's also a grading that is compatible with the taking tensor product of complexes and then taking the total complex of the tensor product, and that is what you need in order to make to do a regularization scheme that is compatible with the tensor product structure. Anyway, so you get a big sum, and if you look at this big sum clearly converges if T and Z are both less than 1, and it converges to a nice rational function. This third line, relatively nice rational function in T and Z. And this rational function I clearly can specialize to T and Z to 1. I just set it to 1. That's fine. And if I do so, then it in fact simplifies even further to this quite pretty identity at the bottom here. So this is the resolution idea. And now you want to resolve Verlinde's formula, and now we are a little bit more precise. So in the general setup is you need a VOA you are interested in. It has to admit a conformal embedding in a VOA that you do understand. So our example is V is SL2 at admissible level, A is this Virasoro times pi. You need to know that this good VOA A has a semi-simple vertex tensor category that is nice. And for V, you need you need to know that it has a tensor category structure. Then you need a bunch of assumptions. Basically, it is that your good VOA already has a Verlinde formula, that the VOA itself, and in fact, here I did overkill. Point 2 can be replaced, that the VOA itself can be resolved by objects in D, and then certain conditions that ensure a sensible notion of regularized quantum dimensions. Really, what you need to do is you have to find a regularization scheme that is compatible with taking total complexes of tensor products of complexes.
Thomas, do you need rigidity as well?
In fact, it turns out I need a few more conditions, and these conditions are exactly the ones of the paper with Kenichi, Harshit, and Robert that imply rigidity.
Thanks.
Because it's a very good question. This more is it's a quite a technical thing, and from the technical point of, so first of all, I actually don't need rigidity. I only need flatness of tensor product, because without flatness, I don't have a sensible notion of Grothendieck ring. But of course, everything is prettier with rigidity. I don't want to conjecture anything here, but sloppily said is that every VOA that one would like to declare to be not pathological in some sense should allow for such a setup. I think this, what I want to say is this is, I do see that this should be a very generic feature, and so I want to claim that very much like we now have a sensible notion of finite VOAs with good finiteness conditions, namely C2 cofinite and rational, together with contragradient dual, self-contragradient dual, blah blah blah. I would like to say that somehow a similar, but of course more sophisticated setup should also exist in the non-semi-simple setting. Now, the setup is, of course, now we need a notion of S-kernel given by the modular transformation of the irreducible module of the good VOA. So D stands for the good VOA. That allows us to define quantum dimensions of the good VOA. And then the point is just having this resolution of the VOA of interests itself allows to extend this notion in the first place to the VOA of interest. Whether it makes sense is of course not clear yet. And now because you want to have an integral formula, you have to you of course need to be able to integrate. So that means the space. So the set of irreducible D modules is a space, and that should have a certain measure so that you can integrate your S-kernel entries against suitable test functions, and the suitable test functions are, of course, the characters. And what you require is that this S-kernel satisfies unitarity. This is really already something that is included in the, if you want, in the definition of Verlinde's formula. And if you have this, you can define the Verlinde algebra of characters as this double integral. So if I were to go back 20 slides, then you would see that this is exactly the formula that Verlinde already had, just sums replaced by integrals, and because finite sums have no big convergence issues, I don't need to phrase it in terms of characters, but because I do an integral, I also need to integrate against something, and there the characters are the good thing. Good, my theorem is that under the setup, where of course I haven't been totally clear about the assumptions, is good enough that indeed that this so defined product on the space of characters gives you, respects the tensor product of the modules of the vertex algebra. In other words, Verlinde's formula is true. Okay. And that means in particular, my 12-year-old, so at the time I wrote it, 11-year-old conjecture with David is true, and there was a similar conjecture that I wrote down with Anton Milash, and David and Simon Wood, I think, had similar ideas, but not quite on that. Anyway, and that was phrased a bit different, but the theorem is good enough that both these conjectures follow immediately, and that they follow without big computation. So these are computations that take you maybe for each example 2 days or so. To give you an example of what the fusion rules look like, you get formulas like this. And if you were just to look at the free field algebra, then you would only get the very first summand here. So just to illustrate, the fusion rules of the affine VOA are much richer than of the of the free field algebra. Good. I'm good with time today. So thank you very much for your attention.
Thank you, Thomas. Let me stop the recording so we can ask more questions. Thank you so much.